So first I want to talk a bit about what concurrency means as a general phenomenon in geometry. To me, I think of it as the difference between something that we expect generically will happen, something that will happen most of the time, versus something that I like to think of as making headlines, making the news, something that doesn't always happen, and so when it does, it's something special. To give you a feel for what that looks like, let's think about what it takes to take a set of points and ask the question about whether those points lie on a common line. The answer to that question depends on how many points we start with. If I start with 2 points, let's call them P and Q, then as long as P and Q are not the same point, in other words, on top of one another, then we know that there's one and only one line in Euclidean geometry that we can draw through those 2 points. That's always going to be the case, again, as long as P and Q are not the same point. And so the condition of 2 points lying on a common line is what we call a generic condition. The set of conditions under which it doesn't hold is very uncommon, the 2 points lying on top of one another, for example. So that's not a very special happening for 2 points to lie on a common line. On the other hand, as soon as I have 3 different points in the mix, let's call them P, Q, and R, then in general, if I place those 3 points randomly on a piece of paper, there will not be one line that goes through all 3 of those points. So do they lie on a common line? Probably not. And so it's going to take a feat of luck for us to take 3 points that I randomly select on a piece of paper, and for those 3 points to lie exactly on a common line. If that does happen, it's a remarkable event, and we call that a concurrency of these 3 points. So if I have 3 points just randomly thrown onto a piece of paper in what we call general position, then I can't expect them to all lie on a common line. But if they do all lie on a common line, 3 points being collinear, that's something special. It doesn't happen very often, and so we call it a concurrency in geometry. The same is true if I take lines in geometry, in Euclidean geometry, and ask if they have a common intersection point. If I start with 2 lines, let's call them L and M, then as long as those lines are not parallel in Euclidean geometry, they will have one and only one intersection point. And so it's generically true that 2 lines in Euclidean geometry have a common intersection. But that's not the case if I draw 3 lines at random, L, M, and N. They probably don't intersect at a single point. And so if they do, this is something remarkable. Here's an L, M, and N that intersect at a common point, and that's again called a concurrency. This is something that we can't generally expect to happen, and so when it does, it makes the headlines for us. Just for an example in a higher dimension, let's think about replacing line, in the first example that we did here, with plane instead. So if I have a set of points, what are the chances that those points lie on a common plane in 3 dimensions? Well, if I just have 2 points to start with, then we already know that 2 points generically, as long as they're different points, lie on one and only one line. So generically, there's a line that goes through these 2 points, P and Q. And that line can be part of a plane that then contains those 2 points. But there's more than one plane that contains that line that contains our 2 points. I could choose a whole lot of planes with different orientations. There are many different choices of plane that I could sketch here that contain the points P and Q. So not only is it a generic condition that 2 points lie on a common plane, there are in fact a whole bunch of different planes that we can choose from that would satisfy that condition. If we go from 2 points up to 3, things get a little bit different. If I pick 3 points in general position, that means that the 3 are not collinear with one another and they're not on top of one another, so they determine, in Euclidean geometry, a unique triangle. And if I take that triangle and I extend it out to the ends of the horizons on all sides, I get a plane that contains that triangle. And that again happens generically. If I have 3 points and I just place them randomly inside a space, they will determine a plane. And the plane they determine, in general position, there is only one choice of that plane. You might have done problems like this in vector calculus, where you're given 3 points in 3 dimensions, and you have to find an equation for the plane that contains those 3 points. So there's only one answer for what plane contains a set of 3 points in general position, but there is such a plane generically. The only time there might not be uniquely defined is if the points are on top of one another. And so we only get something interesting here if we move from 3 points to 4. If I situate 4 points inside of space generically, in general position, then those 4 points are going to determine a tetrahedron, a 3-dimensional object in the kind of the shape of a pyramid-like object, if you like. And probably it's not the case that all 4 of those points lie on a common plane. But if I somehow manage to get a miracle, and that third point lies in the plane, the 4th point lies in the plane determined by the first 3, that's a surprise. That makes the newspapers. That's a headline. That's a concurrency of these 4 points when those 4 points are coplanar. So the moral of the story is that concurrencies are exceptional events in geometry. They happen when, for example, 3 points share a common line. Doesn't happen that often, even if it does with 2. Or when 3 lines share a common intersection point. Again, it happens generically with 2 lines, but with 3 lines we can't expect it to happen always. And likewise, when 4 points are coplanar, when they share a common plane. We can't expect that generically to happen, even if it does generically happen with only 3 points.